Welcome to another class. Here we'll be talking about organic structures, just an introduction to organic structures. As we all know, organic chemistry is the study of molecules. It is the study of molecules that filter around the element carbon. Then carbon actually is a special atom, very special. It's a special atom because it has this excellent way of connecting with other atoms, and that property we regard it as catenation. So it's a property of carbon, making it very much special because it has an excellent property of being able to coordinate with other atoms, right, including carbon itself, to form strong chains or complex structures. And that is why the backbone of almost any molecule found in living things is carbon. Basically everything is composed of carbon. So now, how does carbon be able to coordinate or form bonds with other atoms via catenation? What makes it possible? All right, how does that happen? It happens through process we call by covalent bonding. Through covalent bonding, carbon is able to coordinate with other atoms, right, giving it that property to catenate. That is catenation, right? Now, atoms itself, they are held by the sharing of tiny, let's call it tiny particles called electrons. That is how atoms are actually held. They are held together by sharing tiny particles called electrons. So now, covalent bond, as we just implied here, think of it like a handshake when two people are about shaking their hands, all right, between two atoms. So it's more like a handshake between two atoms where they each share one electron to form a pair that holds them together. Now I'm going to explain this structurally so that you understand exactly what I'm trying to say. And this is where you have to pay very much attention. If you grab this, you're definitely good to go. So just an introductory, all right? So I'll make use of carbon, just as we've been emphasizing, was the electronic configuration 1s2, 2s2, 2p2, right? So if we want to distribute it, so this is 1s, this is 2s, this is 2p, it's 3, okay? So basically 2p is 2px. We'll still come to this later on in this course when we start discussing hybridization. So basically I'm going to give an insight for you to understand that concept called hybridization and its true covalent bonding, and that is why carbon is able to coordinate with a lot of atoms. All right, so now carbon is atomic number is 6. Carbon is more like this 666. All right, 6 electrons, 6 protons, 6 neutrons. All right, so how many electrons do we have? 6. So we're going to distribute these electrons across the various orbitals. All right, and according to Hund's rule, the electrons must fill singly. So 1, 2, 3, 4, 5, and 6. So you can see this is how we represent it, all right, by following Hund's rule. Now, if you look at the structure, these two orbitals here are the valence, they make up the valence shell. You have to know that. So how is this even the valence shell? That's what you could be asking yourself. Now you should know that we have the K shell, then we have the L shell, right? And the K shell maximum is 2 electrons, as you can see here, The S shell can contain 8. So if we have 2 here, these 2 you see here, there are these ones right here in the first shell. So we are left with 1, 2, 3, 4. So I'm going to have 1, 2, 3, 4. Can you see that? Which stands for this one, this one, this one, and this one. All right. So with that being said, carbon is always looking for a way to satisfy this electron, this electron, this electron, this electron, and that gives it its ability to catenate. That's to form a lot of bonds with other atoms because it is tetravalent. 1, 2, 3, 4. All right, this is 1, 2, 3, 4. Now, as you can see, these 4 electrons are at the outermost shell, which is the L shell, and that is why I said what you just seen here, these regions here are the valence shell. That's basically what it means. Now we will look at how carbon is able to form, the bonds. We're going to be looking at sigma bond. We're looking at the pi bonds. That's double bonds and triple bonds. How is this possible? And this is through what is called hybridization of orbitals. All right, so basically, let's take for example, let's start with the double bonds. That's the alkene. So I'm not going to wipe. Probably I should wipe this away. Okay, let me wipe this. I believe you could be taking some notes. So if we want to account, why do we have carbon to carbon double bonds? What kind of hybridization takes place? What kind of overlap of atomic orbitals take place? That's what we want to find out. So how come about this? Now, previously, if you've taken the notes, we had the 1s orbital, we have 2s, then we have the 2px, 2py, and 2pz, right? You could see the shapes over there, but then let's continue. So we already filled this to be like this, right? So now take this particular one to be that of the first carbon, which is this carbon. This is the configuration, okay, for the first carbon. So in that case, for the second carbon, which is this one, all right, I'm going to represent it with this. But first of all, let me use this for the second carbon so that you follow up. So if we have this one, we are still representing the same carbon. All right, so we have this, we have this, we have this, and this. You know where we got all this from? 1s2, 2s2, then we have 2p2. Remember, these are the valence shell. Now, which is this one? Can you see? 2 plus 2 is 4. Or how many of these electrons do we have? 1, 2, 3, 4. The same thing over there. So it's the valence shell. That is agreed. So let's continue. So if carbon is going to form a bond, if this one is going to form a bond with this one, according to Valence Bond Theory, it implies that, let me show you something here. It implies that this is going to carry an opposite spin, all right? That's the only way the overlap will take place, all right? So I'm going to change all of this to carry an opposite spin just to satisfy Valence Bond Theory, all right? So if the bond is going to take place, you remember this is an s orbital, this is p orbital, right? So if this one is going to bond, can you see? So we have 1s, 2s and 2s. That's to tell you I'm going to have an SS overlap, and SS overlap will give you a sigma bond, right? So if you look closely here, this is another overlap can happen here. So each of these overlap forms a bond. So if this overlap should take place, this particular one that I'm just showing, this one, if this one should take place, we are going to have a p overlap, which will give you a pi bond. That is how we came about that. Okay, so and basically remember we are trying to account for double bonds. So in that case, this is 1, this is 1, and this is 2. So we can stop here to show. So it means that these ones that are not the non-bonding electrons, you can see here 2p y and 2p z, 2p y and 2p z. So we're going to have them here and going to have them here. Can you see that? So that's basically it. So then if you look closely again, we can say something about the nature of hybridization. That is the nature of overlap, right? So how many of the s orbital was used is 1. So we're having 1s. Can you see that? This is s. Let me show this. This is s, right? So 1s was used, precisely the 2s. 1s I mean is just single 1s like that. So now how many of the p you can see is only 1, which is this one, okay, which is this one. So 1p was used. So we can have, this is sp hybridization. That's why we'll call this one an sp hybridization. Okay, so that's to tell you carbon to carbon double bond is an sp hybridized orbital, right? So that's how we come about an sp hybridization. 1 electron each from the s orbital of each carbon and that of the p orbital, precisely 2px. Remember we mentioned earlier that the pi orbitals distributed in 3 is 2px, this is 2py, then the other one is 2pz, right? So, and this was the one that got involved from this illustration we've just had. Okay, where do I draw the arrow? This particular one we see here, this one. So you can see here, so that was what was involved in the overlap. Okay, see, it's an 2px. all right, so just 1 electron from the 2px overlap with 1 electron from the other 2px in the other carbon that gave back to the double bond. So we have here a sigma bond, and here we have a pi bond. So that is hybridization for you. So you can do the same thing for the carbon triple bond. We can do the same thing for carbon single bond, and we'll still account for the kind of hybridization. So this is an sp hybridized kind of covalent bonding. So now let's go to another example. Let's see that of methane, which is, single bond. Let's account for that too. So remember, this is an introductory. So when we come to dealing with hybridization of orbitals, you would get to understand it even much better. Okay, now if you look at methane, this is methane, right? We want to get to know the kind of hybridization that takes place. All right, so now we have 4 hydrogens, as you can see here. Carbon is surrounded by 4 hydrogens, definitely attained its octet. Okay, It's octets, meaning that we know that carbon, so if it gets one electron from each of the hydrogens, right, it attains an octet structure, meaning that octet is 8. Okay, so we have 2 electrons here, 2, 4, 6, and 8. You see, and I don't know if you've watched my previous video where we talked about reaction mechanism. Anytime you see 2 electrons like that, they form a bond. Every bond in chemistry is composed of 2 electrons. You should know that. Okay, so, and with that being said, let's continue. Let's continue. So we want to show how the hybridization in methane gets to happen. All right, so I'm going to draw this again, showing how the electrons are distributed. All right, so remember, this is our 1s, this is 2s, this is 2px, this is 2py, and this is 2pz, right? So this is not well clear. This is 2pz, right? So if electron must fill, carbon is 6, atomic number is 6, so I'm going to 1, 2, 3, 4, 5, come back is 6. So we already know the valence shell already. That's the 2x with the 2px, 2py, 2pz as the valence shell, and we've been able to account for that, so that's not a problem. So in this case we have hydrogen, just atomic number 1, so we can just have, and you already know there are 4 of them, so I'm going to have the first hydrogen, right? Remember, it has only 1 electron. Then we have the second hydrogen, remember, 1 electron. Then we have the third hydrogen, 1 electron. Then we can still have the fourth hydrogen, which is 1 electron. All right, so if there's going to be a covalent bonding or sharing of electron, like a handshake between carbon and hydrogen, it just means that we have to respect the valence bond theory. The valence bond theory, remember what he said, that we must ensure that the electrons are of opposite spin. So here I'm going to do it like this: opposite spin, opposite spin, opposite spin, and opposite spin. Can you see that? So I'm going to wipe this off so that you see clearly what I'm trying to do. So if you look closely, remember these are 1s, 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 and 1s. This is 2p. This is no, this is not 2p, this is 2s. So let me put it 2s. So this is 2p, remember to be s, y, and z. So basically what is going to happen is going to be an overlap here, overlap here, overlap here, and overlap here. So now this first overlap here is between an s and an s. Can you see that? So if we have carbon, the first overlap is an s overlap. So I'm going to have hydrogen here. Then you know this is an ss overlap, right? So if you look at this, the second one is an s, like a p orbital, an s and a p orbital overlap. So I'm going to have that here with the other hydrogen. So this is an sp overlap. This one, the next one, as you can see here, is also an sp orbital overlap. So I'm going to have an sp. Likewise, the next one, which is also an sp. Can you see that? So this is also an sp. So basically we have 1 ss overlap and 3 sp overlaps. So, and because of this, this is where valence bond theory failed, because according to valence bond theory, these orbitals are not supposed to be identical. Just take a look. This is an SS overlap. So according to valence bond theory, an SS overlap is not identical to an SP overlap. But this was proven experimentally that all the overlaps, the SS, the bonds, all right, are actually identical, all right, and not different according to valence bond theory. So that was where valence bond theory failed and hybridization came to be. You understand? So what is the nature of hybridization? Now let's look at it. It's quite obvious, right? Now if you look here, just a minute, can you see this? How many S? Only one S was used, so I have S. Now if you look at these ones, how many of the P? We have 1, 2, 3, P3. So you see, it is sp3 hybridized. Okay, so this is basically what I expect you guys to get acquainted with, so that when we go further into dealing with hybridization, you would understand better. All right, so I'm going to leave the one for, I think there's a one we didn't get to treat, right? So I'm going to leave that off. We treated which did we even do last before this one? Was it a double bond? Yeah, we treated that of a double bond, where we said that it is sp hybridized, right? So, and we've done that of an sp3. So I would leave you guys with that of a triple. Is it a triple? Yeah, I think, yeah, this is the one I'm going to leave you guys with, so you can try this for yourself and get to account, just get to account why it is sp2 hybridized. Okay, so finally, you need to also know that the nature of hybridization will tell you the shape of the molecule, because these orbitals tend to repel each other, and then they tend to make the molecule have different shapes. We'll go into that even much more in detail subsequently as the time goes. So basically, triple bonds, right, they are always found to be linear. Just take example like this one is also linear. All right, so something like methane is tetrahedral. All right, so they have different orientations. Okay,